Hi, so welcome. And so this is the fifth lecture on PSM. And so let's continue where we stopped yesterday. So, so what I did, I derived the general Sheldon-Lemon expansion on spectral representation for graviton propagator. Now, graviton in generalized sense, so let me call it generalized graviton propagator. In other words, we define gravity as anything that mediates exchange between energy momentum tensors. Okay. So this doesn't have to be Einstein graviton. Anything that mediates exchange between two conserved energy momentum tensors. Now, I will come back how how precise is this definition. Okay, of course, Einstein gravity satisfies this obviously, and many other theories of modified theories. But anyway, I'll comment on this. And so so there is a general representation which we can write as a propagator of the generalized graviton convoluted between contracted with two energy momentum tensors. Let's do it in momentum representation. And so I will okay, there will be overall coefficient, which is not important, which will I have to use this pi's when go to Fourier space and back and forth. Let me normalize it to 1 over m Planck. Okay, and then we have different different structures here. So we have Einsteinian massless graviton that gives tensorial structure of this sort, TT. I mean, T is the trace of the energy momentum tensor. So this is p square plus I epsilon. Let's say I use Feynman propagator, for example. And then there is a sum over massive spin 2 exchanges. So this is m square larger than 0. Okay, sum or a continuum. So the sum could be a continuum or a discretum of this. And they have a tensorial structure which is discontinuously different, because instead of 1/3, 1/2, we have 1/3 there. And then we have so they come with their own coefficients, relative coefficients, which is a spectral, which sets the spectral density. So let me denote them: C2 for spin 2 and massive. Okay, let me call this, denote in this way. And then we have sum over m square larger or 0 of the scalar exchange, and scalar exchange between two energy momentum tensors, scalar that couples with the trace. And so the corresponding coefficient, let me call it spin 0 and m, right? So these are, here they are strictly non-zero, because that's why coefficient is 1/3, and so here they can be anything. So the limit for the scalar exchange between two energy momentum tensors is smooth in the massless limit. Okay. For example, and then we said, for example, if we choose T, the energy momentum, to be a non-relativistic source of mass, some mass m1, let's say if we do this exchange between two sources of the mass of M1 and M2, okay, let's say we have T mu prime. So here also we can have some T and T prime if you want. Prime. Prime. An relativistic source of mass M2, in particular, to get a Newtonian limit of this generalized gravity. Okay, so Newtonian limit. So Newtonian limit we will have so ordinary, and here I'm normalizing it to Planck's square. Then there will be a factor M1, M2. There will be a factor 1 over R, and then there will be some here. Okay, so if I normalize to Einsteinian part, this is Einsteinian part, right? So this is Einsteinian part. If I normalize it to 1, the effect, you can see that for example, the part of Pauli first Pauli part gives, so here I would have m square minus 1/2 of m square, right? So that would be 1/2. And here I would have 1 minus 1/3, so 2/3. So there is 2/3 versus 1/2. So by a factor of 4/3, so there is a relative factor of 4/3, okay? 4/3 of, and we can write it like this, 4/3 for the massive ones. So for m square larger than, so for m larger than 0, okay, we would have, yeah, so the factor C2 and exponent minus mr, and then we have and here we will have factor 2 relative. Of course, these factors I can rescale into C's from the beginning, but just they are useful to observe the relative strength. The one of a scalar is not terribly informative, but the one between massive and massless spin 2s, it is informative because that's a reflection of discontinuity. So here I would have factor of 2, right? So because I would 1/2 versus 1, so now we would have relative factor of 2. So m from 0 to infinity, okay, to arbitrary values, mc 0 of m and exponent minus mr again. Okay, now this exponent minus mr, this is very generic in quantum field theory. In QFT, so any interaction, any gap, any particle with a gap, any mode, any massive mode in a theory with a mass gap, correlators, they die exponentially at large distances. Okay, so this is typical, just manifestation of this Yukawa type potential for gravity. Now this factor of 4/3, so this was the source of precisely this Van-Dam-Weltman-Zakharov discontinuity when they pointed this out. I mentioned this yesterday. Now the thing is that if we only had Newtonian measurements, you could rescale factor of 4/3 in definition of Newton's constant, as you can see from here. But the great thing is that we have different measurements of gravity, and because of this structure, you can see that this structure, once you rescale, even if you rescale into Newton's constant, you can still detect the difference because massive spin 2 and massless spin 2, they interact differently with relativistic and non-relativistic sources. Okay, for example, deflection of light, of the star light from the sun would be approximately 25% different, which is detectable. Okay, if you had a linearized spin 2 particle floating somewhere at the distances of the size of the solar system. Okay, so now let me make a small comment about the equivalence principle. Now here I defined gravity as something that mediates force between two conserved energy momentum tensors. Okay, so such a force would maintain equivalence principle. Okay, because it couples to energy. Okay, so therefore inertial mass and gravitational mass for such a force would be the same. Now there is a interesting. There is it's a side-by remark, but it's interesting. Remember we mentioned Higgs gravity, right? So we said that Higgs also mediates gravity, and so you can ask where is Higgs gravity in this expansion? Okay, well, Higgs gravity has a projection, so on this part, but it's not entirely that part. Okay, why? Because gravity mediated by a Higgs boson, even if Higgs boson were extremely light, would not preserve equivalence principle. Okay, let me just comment on that. So equivalence principle. So equivalence principle in Higgs gravity. So let's take Higgs gravity, right? So we said that the Higgs was mediating gravitational interaction because we took an electrically neutral component of the Higgs boson. So we parameterized Higgs boson as its expectation value. This is the expectation value. 0 stands here for electrically neutral component plus a fluctuation of the Higgs. So the fluctuation of the Higgs, let's not confuse it with gravity. So therefore, let me add here index H. Okay, so this is Higgs. All right, H sub H. So now we had a coupling with fermions, right? So we have Yukawa coupling of neutral Higgs component with fermions of all possible flavors. And then when we plug this expression, we said there is a mass generated for the fermion, psi L bar psi r, plus the coupling with the Higgs boson. So the Higgs boson couples with the same strength as the Yukawa coupling to the fermion. Now this is useful to express as a mass. So let's express it as a mass. So if this is if I call this mass of the fermion, which it is a fundamental fermion, then the coupling of the Higgs boson with the fermion, the strength of the coupling is H psi L bar psi r. The coupling strength is mass of the fermion divided by the expectation value of the Higgs. And we said that the Higgs looks very similar to gravity because the coupling is proportional to the mass. But there is a caveat here. As far as observations are concerned, the question is whether this gravity would, so it looks like it's like Einsteinian gravity, it's like Newtonian gravity. Of course, Newtonian gravity also has equivalence principle. It's purely non-relativistic, obviously, but still, Newtonian gravity tells us that the gravitational strength is proportional, is set by the product of the masses. And so it looks like Higgs accomplishes this property. However, we have to remember the following thing, that this is a fundamental mass of the fermion. Okay, so this is a mass of an elementary fermion at the fundamental level. Okay, so for example, for example, Higgs would couple to coupling to up quark. Okay, so would be coupling to up quark would be proportional to the mass of the up quark. Coupling to down quark would be proportional to the mass of the down quark, and so on. Now, let's think what kind of gravity this would mediate. Let's assume for a moment, and the mass of the Higgs boson is given by the self-coupling of the Higgs boson times the wave. Okay. So we can, for example, take the limit just to make this sharper. Of course, within the standard model, Higgs gravity is a short-range gravity. So Higgs would mediate force of this type. For example, among two fermions, the force mediated by the Higgs would be Yukawa type, right? So potential mediated by Higgs would be minus m psi square over v square exponent minus mr over r, where this is the Higgs mass. Okay, so this will be a short range gravity, but this is not important for this discussion, because, for example, we can take the limit, and to make the issue sharper, we can take the limit when the self-coupling of the Higgs is 0. Okay, we can consistently take this limit in the standard model, and without affecting masses of other fermions. Higgs could be much lighter. Okay, so in that case, Higgs will mediate long-range gravity, let's say at solar distances. But that gravity would not maintain equivalence principle. Why? What is the reason? The reason is that most of our mass, for example, most of the mass of the macroscopic objects consists of is quantum. Why? Because, for example, the masses of the nucleons, like proton and neutron. So let's say proton, right? Let's say proton, right? Or neutron, and corresponding nuclei. They consist of three quarks, right? So they consist of 3 quarks. But the energy of the proton or neutron is not coming from the masses of quarks. The energy of proton and neutron, and the mass of proton, for instance, is much larger than the masses of quarks, or even 3 times masses of light quarks, because the most of the energy of the proton is coming from the binding energy of the quantum binding energy of QCD. So essentially, mass of the proton is quantum in nature. Our mass of the Earth is also mostly quantum in nature. So therefore, the coupling of however, if Higgs couples, so if I think of let's say, exchange between 2 protons by Higgs gravity, the level of, very schematically, the level of Feynman diagram, I can think of like this. I have proton with 3 quarks, and then there is a Higgs exchange of the Higgs. Okay, so there will be diagrams like this, where the Higgs is exchanged among quarks. But the coupling strength of the Higgs is not given by the mass of the proton. It's proportional to the masses of the quarks that are constituents of proton, but not by mass of proton. So correspondingly, the force mediated by the Higgs gravity among nuclei or among particles, different isotopes, which have different compositions of quarks, let's say if it contains different number of up and down quarks, the samples will be different by order 1. Okay, so therefore Higgs gravity would violate equivalence principle, which is okay. It does violate equivalence principle because Higgs gravity is there. It's just very short range. It does violate equivalence principle. That's why Higgs gravity is not precisely the way I defined here gravity as a clean exchange between 2 conserved energy momentum tensors. Higgs gravity has a projection on that. Sure, it also we can express it coupling of the Higgs as energy momentum tensor coupling to energy momentum minus or plus something else, because the energy momentum tensor does depend on the mass of the up quark and down quark, but that's not the dominant. That's not the dominant coupling. Okay, so therefore this is a remark to remember. So for example, if Higgs were massless, gravity, not only the gravity would be much stronger, but also it would violate the equivalence principle. Okay. Currently, there are extremely tight bounds on possible admixtures to Einstein gravity that violate the equivalence principle at large distances. Of course, at short distances, all these measurements are done at macroscopic scales larger than millimeter, and so on. Or okay, the best measurements I think are from Adelberger and the collaborators from University of Washington. At the shortest scales, Newtonian gravity has been checked like around 10 microns or 100 microns, something like that. But the equivalence principle tests are long distance tests, and this is something to remember. So therefore, Higgs gravity would not be like Einstein gravity. Are there any questions about this?
I don't see any.
Okay, so here let's say we have quarks. I don't know, UD, UDT, let's say, or UU. Let's make it proton. and so on. Okay, I don't hear any questions about this. Okay, so let's move on. Now, this Shannon-Lemon expansion, I said that this is extremely informative. It's a simple fact. So this is one of those things that QFT that demonstrates extreme power of quantum field theory, and in particular effective quantum field theory. That a simple requirement of causality and analyticity can give you extremely powerful statement about how theory should behave at different length scales. Now, as we already mentioned, one important conclusion from here is that because of the positivity of spectral representation, all these coefficients must be positive. In other words, they must have the same sign as once we normalize the Einstein gravity to be attractive as it is. Okay, so they have the same sign. In other words, this statement is equivalent to saying that all the elementary exchanges that contribute into whatever generalized gravity you have, they carry positive norm. They carry positive norm and positive energy. Okay, so now departure from this condition, if we would make some of the constituents, some of the entries in this spectral function negative, this would be equivalent of having in a theory a mediator with ill-defined norm. I mean, with non-positive norm, or sometimes you can trade norm for energy and non-positive energy. But quantum field theory cannot afford this, okay? So therefore, consistency of quantum field theory unambiguously tells us that gravity is attractive. At short distances, it becomes more attractive, okay? We cannot make gravity less attractive. So the strength is set by this expansion, by this expression. So in other words, schematically, to understand what this means is, okay, so yesterday we gave some pictures here, right? And so for example, let's say this momentum transfer, and this is effective strength of gravity, alpha gravity, of course, in generalized sense, alpha gravity meaning, okay, if I have exchange by generalized graviton, this is the effective strength, okay? This is the effective alpha gravity, what it sets, okay? And so here is one where this canonically normalized generalized graviton would hit the strong coupling. And so in Einstein gravity, this happens at the Planck scale, okay? So in pure Einstein, if we don't have other species, we only have graviton with two polarizations. So this would, gravity would do this, okay? So it would, sorry. So it increases, and then very quickly, pretty quickly, it increases to, and hits 1, okay? Now, this essentially is a boundary, as we discussed. Within a theory that within Einstein gravity, we cannot have momentum exchange between gravitons which exceeds the Planck mass. Okay, I'll come back to, as we already mentioned. I'll comment on it in a moment. But what this picture tells us is that now in generalized gravity, what may happen is that cutoff can move down perfectly fine. So in other words, gravity can become more attractive, and so it can reach 1 at lower scale. That's perfectly okay. So it's Einsteinian, and then at some point it can reach the scale. So the transition may be smooth, okay? So in other words, the deviation from Einstein gravity can already set at the level where gravity is weakly interacting and classical, or also transition could be pretty sharp. So the new degrees of freedom can open up very close to the cutoff. That can happen. But this is what should happen as long as you are within the consistent effective field theory of gravity. Now, what cannot happen is, and this is an extremely powerful and important statement, what this Chern-Lemon expansion is telling us, what cannot happen is to make gravity weaker before it hits the strong coupling. In other words, before the theory goes out of the validity of effective field theory, you cannot make gravity weak. So in other words, there is no way to have any behavior of, for example, of this sort. Okay, so for example, something like that, and then going down. This is not possible, because this behavior would imply that some of the coefficients of spectral representation, or the spectral representation of generalized graviton propagator, somewhere has to become negative. This means that theory contains a pathological degree of freedom, which cannot have a, sometimes we call them ghosts, but okay, the name doesn't matter. But these are not Faddeev-Popov ghosts. These are real. This would be a real physical ghost, meaning that within quantum field theory, we cannot work with this kind of objects. And that's the power of quantum field theory, because quantum field theory is more restrictive is the theory, more powerful it is. Okay, because it allows you less freedom. So therefore, it's more predictive. And but by the way, once Ed Witten said in a very compact way that the reason we make progress because most of the things do not work. So this is one manifestation of that. Okay. So therefore, more powerfully a given theory kills different possibilities. That's better, because then it's more restrictive. Okay. Now, so this cannot happen. So therefore, okay, I mean, you could say that what could happen is that this hits the strong coupling and then goes down. But you see, if once the gravity hits strong coupling, then the theory changes the regime. And of course, then it's a separate story what goes down. But this means that, in other words, what is a very important and powerful statement is that we cannot avoid within effective field theory hitting the strong coupling of gravity. Okay, within effective field theory. We can avoid it by moving gravity towards different regime. For example, this is also what happens in Einstein gravity, as we discussed, right? So in Einstein gravity, if we try to, let's say we have some scattering experiment, right? I don't know, we scatter 2 gravitons, and we want to, we scatter 2 to 2, and so we increase the momentum transfer, okay, in the process by increasing energy in the collision. And suppose you want to now make momentum transfer larger than the Planck mass, okay? So you want to make Q much larger than the Planck mass. And well, of course, you have to increase center of mass energy for this. And increasing center of mass energy inevitably puts you into the regime where the moment, instead of being dominated by high momentum transfer, the scattering amplitude becomes multi-particle scattering amplitude, with momentum transfer per particle being lowered down, because of, you can interpret this as a black hole formation. So in other words, what happened if you try this? Of course, if you try this, you have to increase center of mass energy. Usually we denote it by square root of S. You have to increase the trans-Planckian. But then what happens is that the scattering is dominated by multi-graviton production. And so the momentum transfer goes down. So there is a, of course, I mean, by now there is a strong evidence, pretty strong evidence that this is the way unitarizes itself is not a proof, obviously, but there is a strong evidence that these type of amplitudes, they are the ones that saturate unitarity in Transplanckian domain. So therefore, there are indications that actually the maximal momentum transfer that we can have in gravity is in the Planck mass in pure Einstein. If cutoff is lower, consequently this scale can be lowered. In pure Einstein, maximum we can do is to have momentum transfer Planckian, and above that things become softer. So somehow, yeah. And the other day we had a discussion, right? That was the question Francesco was asking a question about. So yeah, all the evidence indicates that this is the one particular domain around momentum transfer and Planck, which we don't know what to do with, how to compute it, okay? Because there is no obvious perturbative parameter in which we can do expansion. So this is one domain. Now, this may sound like an easy point because, oh, very great. I mean, there is only one point where we cannot control the theory, but it's an extremely important point. So therefore, of course, it's very encouraging that what gravity is telling us that here there is no problem in the low momentum transfer domain, and in the high center of mass energy here we have black holes. This is dominated by black holes or by other extended objects. If you embed gravity into string theory offers the possibility to supplement black holes. Not to supplement, but to supplement, to additionally give you a possibility to have extended objects softening the amplitudes. Yeah, I mean, about Veneziano amplitude, and at least you have heard about it, by means of producing extended objects, vibrations of the extended objects. Okay, but even if you don't have that, even if gravity is pure, pure gravity offers you this black hole domain. Okay, for sort of self-unitarizing at very high center of mass energy. But this point is there, and we need to understand something about this point. And all the discussions, remember, I mean, all the story about hierarchy problem and stuff like this hangs on that, okay? Now, of course, these are not lectures on UV completion of gravity, obviously, or lectures on black holes. But now you see that these issues, hierarchy problem is such a deep question that it is intrinsically linked with these issues. And we cannot discuss problems that are problems of cutoff sensitivity without having any idea what we are talking about. So that's why these discussions are necessary. I don't know, otherwise I don't know how to discuss the hierarchy problem and how to take it seriously without this underlying very important information behind it, okay? All right, so I don't know, are there any questions? Yeah, there's a hand, Alvaro.
Yes, hi. So if you want to understand the contributions of gravity to matter, let's say to the running couplings and so on, what you're telling is that you cannot computing like the first order contributions of gravitons to the endpoint functions of the matter fields is not sufficient. So you necessarily have to go beyond non-minimally coupled gravity. Am I understanding correctly? Like how do I understand the black hole contributions in the critical regime at the Planck scale?
Yeah. So in other words, okay. So let's try. Yeah. Thanks for this question. Let's try to make this issue more precise. I mean, strictly speaking, I didn't enter into those discussions. I didn't enter into a discussion, for example, if I have a standard model and let's say I have renormalization of the wave function of an electron, how graviton contributes into this renormalization of the wave function of the electron. But of course, these issues are connected with the issues of UV completion of gravity, obviously, because the problem with virtual gravitons is that virtual gravitons, sooner or later, they have momentum comparable and energy and momentum comparable to the Planck mass. Correspondingly, even if real gravitons do not enter in strong coupling regime in Einstein gravity, right? the virtual gravitors, they always probe the strong coupling regime because they are virtual. So correspondingly, okay. So therefore,
sorry, if you want to approach the hierarchy problem and the contribution of gravity to the hierarchy problem at the Planck scale, I mean, you would, I mean, what I'm understanding is that you are saying that you have to look at the black hole contribution, black hole effects on such.
Yeah, I'm getting there, right? So you probably noticed that I'm trying to structure the discussion in the way that discuss things that are sufficient and more or less unambiguous and clearly understood. There are other issues which are, of course, there are infinite number of questions about quantum contributions from gravity into the loops, etc., okay, which also add to the unknowns, right? So now there is a general. So what I was saying to the following thing, right? So there are facts that we know about Einstein gravity, and which we cannot ignore, okay? And then I try to use these facts as guidelines. Then, of course, there are unknowns, which we don't know how to take them into account, okay? And this only adds to the question, okay? It makes the question even sharper. Now, so far, what I was saying, what I was trying to explain is that in gravity, there is a sharp cutoff, which is either Planck scale or m star, depending in which theory you are. But no matter what, gravity has a cutoff which is less or of order the Planck mass, cannot be above Planck mass, because if you are staying within again, I'm saying, if you are staying within effective field theory, if you introduce some alternative framework, by the way, string theory fully agrees with this. But I'm saying because string theory plays the same rules as field theory. String theory is not violating any of the rules of causality or unitarity or anything like that. Now, as long as we stay in the framework that we understand, which is effective field theory framework, this is the story, and this is what Chell and Lemon expansion of spectral representation tells us, that cutoff where gravity hits the strong coupling is Planck scale or below the Planck scale. Okay, so now this, and the next information that gravity is telling us is because gravity has this UV-IR connection through black holes, that if you make something very energetic, instead of it, not only that you are probing short distances, but you are probing also large distances because the Schwarzschild radius grows. Because of this, gravity forbids this region for elementary particles. We know that you cannot have elementary particle in a theory that flows to Einstein gravity in deep infrared. You cannot have an elementary particle which is arbitrarily heavier than the Planck mass. This is not possible. This is a fully non-perturbative statement. And this statement is sufficient for us to understand that there is a non-perturbative cutoff on the mass of any elementary particle. Okay. Now the question is, now there's a second question. So this information also tells us something very important. What is this very important information? This tells us that once I couple standard model to Einstein gravity, or even if I introduce pure Einstein gravity, there is no way to say that my only degree of freedom is graviton, or the only degree of freedom are standard model particles plus graviton. Why? Because at the Planck scale, because above Planck scale we have black holes, and somewhere these black holes. So if I approach from below, I approach from the particle domain, right? So particle, and if I approach from above, I approach from the black hole domain. So if I take a black hole and try to make its mass smaller and smaller, okay, so I have a black hole of mass m. Sure, I can start with black hole of mass m, much heavier than the Planck mass. This black hole is a very good in a very good approximation is classical, as we already discussed. Why? Because entropy of the black hole, which is m over m Planck square, is much larger than 1 for this case. Correspondingly, the corrections, which are 1 over s corrections to the physics of known physics, semi-classical physics of a black hole, they are small, at least for initial times. These I already discussed. Okay, now, however, if I take m towards m Planck, obviously the 1 over s corrections become important. At some point, we don't know where that point is. I cannot tell you that that point is at twice m Planck or 3 times m Planck or m Planck divided by 4 pi. Unfortunately, I cannot tell you that. Nobody can tell you that, okay? But we know that somewhere here in this domain, this black hole loses properties of a black hole because it becomes more and more quantum, okay? And acquires properties of elementary particle, okay? But the issue is that this object, an elementary particle or a black hole with mass m Planck, is neither a black hole in the usual sense, nor an elementary particle. You cannot define, for example, for such a black holes, geometric notion are meaningless. You cannot define the horizon or anything like that because 1 over s corrections, fluctuations are very important. For example, if you naively apply Hawking evaporation law to this black hole, it will just explode. The explode within the time that is equal to its size. So this black hole, from all that we know, all experience we have in quantum field theory, such a black hole is a broad resonance. So it becomes a resonance which decays very quickly, okay? So therefore, now the question is what to call this object, okay? Should we call it, we cannot really call it an elementary particle because it's on the boundary. We cannot call it a black hole because it's, again, because of the same reason. So we called it quantum black holes. For example, in large extra-dimensional papers and stuff, we would use term quantum black holes. I like that term. Okay, so we can call it quantum black hole, or we can call it something else. Okay, but that's a beginning of a black hole tower. So in other words, if you so therefore, but why is this important? Because this information is important because this tells you that in pure, even if you are in pure Einstein gravity, you will face this the existence of these objects because you have black holes from one side, particles from the other. In between, there is so there will be some resonances, some quantum resonances, with the mass of order the Planck mass. This is what I call quantum black holes. Okay, so now the thing is, if I'm now doing some computation in the standard model, let's say I want to compute Higgs mass, correction to the Higgs mass, right? The computation, this computation, okay, sooner or later I need to answer a question. What is the contribution from these quantum black holes in this process? So we don't know that because we don't have a technique to compute this. We don't have any powerful methods to compute contributions from the objects whose mass is of order the cutoff. Putting aside quantum gravity, we don't even know how to do that in ordinary QCD, right? In ordinary QCD, we have the same problem, despite the fact that we have QCD scale, right? So despite the fact that in ordinary QCD, we have a fantastic theory here, asymptotically free theory of gluons and quarks. And we have theory of effective theory, chiral Lagrangian, for example, here pions, and so on. Here, at some scale, perturbation theory breaks down in both expansions. And as you know very well, despite having a theory, renormalizable theory, we can't even predict, we can't even compute, for example, a global spectrum in QCD, all right? Now, therefore, it's not surprising that we have a similar problem at the Planck scale, okay? So it's of the same type of a problem. And that is, at this level of understanding, we cannot avoid this problem. And that only adds to the unknowns, okay? So this is basically the important message. Correspondingly, any question about ultraviolet sensitive quantities, such as the Higgs mass, okay, unless we have other guidelines, some non-perturbative guidelines. And by the way, if I'll have time, maybe I'll comment about cosmological constant, because for cosmological constant, we have such a guideline actually, okay, S metrics. This is different. But here, okay, we don't. And so and the ultraviolet sensitive quantity faces this fact, how to take into account this cutoff contributions from the cutoff, because theory is strongly interacting there, okay? This is very different from other threshold corrections. For example, if you have a new particle, if you introduce a new particle somewhere, for example, supersymmetry or a new particle, okay? So that's different because I can introduce a new particle, I can integrate a new particle here while theory is still weakly interacting, and compute the contribution from new particle. These are usual threshold corrections. For example, already in the standard model, when we go about the energy of top quark mass, we integrate in top quark mass and so on. This is not an issue because we have a theory, this is weakly interacting theory, and we can do computations there. Okay, so it's a separate issue. But here the issue is much sharper. Does this answer your question? Okay,
yes,
very good.
Thank you very much.
All right, very good. Okay, anything else? Okay, I don't see any other questions. So very good. So now, okay, let's come back to the story with this transition. Okay, here, right? Now, okay, let's use the same picture, not to plot a new picture. So now we know one situation when theory forces us to do this, okay? To have cutoff which is lower. This is if we have sufficiently large number of particle species. By the way, already in the standard model, we have a pretty large number of particle species. Number of particle species, if we count all the spin polarizations, they have all to be counted, is around 100 something already in the standard model, okay? And so in the extension of the standard model, usually the number of species is larger, but we don't know how many hidden sectors are there, etc., etc. So if we have certain number of particle species, we know that this must be happening. So the question is, how is this happening? This can happen smoothly because the increase could be smooth or soft transition, okay, like that. Or transition could be sharp or hard. Okay. So in other words, towards the cutoff, okay, when we have large number of particle species, cutoff is lowered, and the transition to the strong coupling regime could be very sharp. The new degrees of freedom may open up very close to the cutoff, or the transition could be sufficiently smooth and soft. Okay, and this sharpness and softness is reflected in the spectrum of these objects that contribute gravitational degrees of freedom, that contribute into the in channel lemma expansion, okay, of the graviton propagator, a spectral representation of the graviton propagator. Okay, so the gravitational degrees of freedom can be spread out, weakly interacting, many of them soft, and give sharp and give smooth transition, soft. So which means that already being in effective field theory, the gravity while weakly interacting, departs softly from Einstein gravity. Okay, gradually departs and then reaches the strong coupling, accelerates the growth. Or the new gravitational degrees of freedom may open up very sharp, close to the cutoff. Okay, these are the regimes that we can cover in effective field theory. Now, of course, there can be regimes which are intrinsically not understandable in terms of effective field theory. Intrinsically, for example, require immediately to understand in terms of multi-particle or extended objects and so on. So, right. but I will focus on the ones that we can understand within effective field theory. Okay, the transition. All right. So this type of smooth transition, for instance, is offered by extra dimensions, in particular by large extra dimensions. Okay. Now, this is, of course, regardless, whatever I'm saying here, this applies to arbitrary number of particle species, to arbitrary number of, but of course, if you want to have a cutoff, if we want this to be relevant for the hierarchy problem, for addressing the hierarchy problem, for hierarchy, problem, of course, the cutoff should be around few TeV. Okay. And correspondingly, if this lowering is because of number of particle species, either gravitational or non-gravitational, but gravitational species must accompany non-gravitational species to make gravity strong at the cutoff scale. So then the number of species should be around 10 to the 32. Okay. So it should have, by the way, this is also an upper bound on the number of species so that we can have in our theory. Okay, so this is very interesting. In other words, the fact that gravity lowers the cutoff when you introduce number of particle species, and the fact that we have not seen any quantum gravity effects, strong quantum gravity effects, up until LHC energies, tells us that this is an absolute upper bound on the total number of particle species that can exist in the theory. Okay, total number of propagating particle species. This, if you think it like this is an extremely powerful bound, because naively you could say there could be infinite number of hidden sectors. Okay, why not? But this number, although it's very large, it's still very relatively small. Okay. Now, this number, the extra dimensions give us this number for free. The extra dimensions, they give us this number, large extra dimensions, they give us this number even without noticing this number explicitly, because it's hidden in the volume of extra space. Okay, as I will discuss now. All right. So let's see. We can. So let me take questions, and then we can make a short break. If there are any questions about this so far, and
yeah, I have a question. So before you say that, I mean, you're arguing that gravity is essential to pin down sharply this problem, right? This is you're using this to provide a scale which is you cannot run away from, right? But right. You still agree that even without gravity, if you do have a scale, the problem is defined even in a different effective field theory context without gravity, right?
Yes, thanks very much. Yeah, absolutely. Yeah, this is this is an important question, because I don't want to create false impression. Maybe I should have been very clear about that. So indeed, by no means you should understand. Since I give importance to gravity, you should not think that I'm saying that the problem can be dismissed if we don't have gravity. Okay, I'm not saying that. There are people that are saying that. Okay. So indeed, so hierarchy problem is there whenever we have. So you see, imagine we don't have gravity, right? But we still know that standard model is not a full story, because okay, even if so, first of all, there is a Landau pole. We know that something must happen before extremely high energies. Okay. In the standard model. So, but in any case, I mean, we know the standard model requires some scale where it is embedded in more powerful theory. And since there is a scale, even if that scale has nothing to do with gravity, that scale already is there, and you can already define hierarchy problem relative to that scale. Okay. Or if you have some other particles, for example, grand unification or some other scale in the problem introduced in the problem. So in other words, what I'm saying is that it's very, from at the present level of understanding of QFT, at least the level of my understanding, it's unimaginable that standard model is a theory without a cutoff. Okay, and correspondingly, since there is a cutoff, gravitational or non-gravitational, if there is a cutoff, there is the issue of sensitivity towards this cutoff. The cutoff, as I said, as Francesco noted, cutoff could be a particle, a new particle, some new interaction, and so on, or something more sophisticated, which requires unitarization of the standard model, or completion of the standard model at very high energies. But absolutely, yes, the hierarchy problem, I take it very seriously, even without any gravity. But I'm just saying, gravity provides a very explicit, gravity makes the issue very sharp, because it makes this fact that elementary particles masses are simply cannot be arbitrarily large, it provides it very explicit and non-perturbative. Okay.
Perfect. Thank you again.
Okay, thank you. All right, if there are no other questions, let's make a 5 minutes break, if you don't mind. So let's say we see each other in yeah, literally 5 minutes, if you don't mind.
11:02.
Yeah, 2:11. Sorry to be so precise, but okay, this last lecture I want to fit some information. Okay. Okay, see you shortly. Okay, so so now let me illustrate, just to give an illustrative example, how how extra dimensions do this. Again, in quantum field theory, we think in terms of degrees of freedom. So therefore, if you want to lower the cutoff of gravity by introducing properly degrees of freedom, strictly speaking, all you need is this, just to have new degrees of freedom. But extra dimensions, the language of extra dimensions is nice, because that gives it a geometric meaning, and a nice geometric meaning. So let's consider the story with extra dimensions. I mean, I will assume that they are large. Oh, okay. So I will just follow the minimal framework that we had with together with Nima Arkani-Hamed and Savas Dimopoulos as a sort of as a general framework. Then we can deform it and modify. Okay, so I will start with one extra dimension for simplicity. So let's say, and generalization is trivial, I just want to convey the concept. So let's say we have a theory in which we have 4 space-time dimensions, x mu goes from 0, 1, 2, 3, and then we have a 5th dimension. Let me call it x5, not 4, but 5. Not to confuse with the Euclidean time. We can also denote it by y. Okay, so there is this. So let's say now think in the following terms. Imagine that we have 2 observers. So okay, Bob and Alice, and so Bob is observer on that thinks in terms of 4-dimensional coordinates, and Alice is a fully high-dimensional observer. Okay, now, okay, here's Bob, and here's Alice, and so there is a graviton in this 5-dimensional theory. So there's 5-dimensional gravity. So graviton, 5-dimensional graviton can have momentum. So the total, the coordinates that grow from 0, 1, 2, 3, 5, I'll denote by a, xa. Xa are coordinates that include x mu and y. So a goes from 0, 1, 2, 3, and 5. Okay. And so this graviton has projection of momenta in y direction and has projection of momenta in 4 dimensions. And for as we said, the dispersion relation of this particle from the point of view of Alice is just a dispersion relation of a high dimensional massless particle. So the high dimensional momentum PA being 0, but the same thing by Bob is seen as, and so since Bob cannot measure Py, Bob can think about this Py as a mass, okay? And so correspondingly, dispersion relation is dispersion relation of a massive particle. Not only one, but infinite number of massive particles, formally infinite number, because the momentum in extra dimension can take different values, okay? So for the same momentum in 4 dimensions, you can have all possible momenta in extra dimensions. And so the 2 observers, they see the same physics, obviously, okay? But they interpret it in different ways. Okay, so now let's say that Alice has, so Alice is looking at linearized gravity in 5 dimensions. So let's take a free graviton, HAB. This is 5-dimensional graviton. It depends on coordinate x and y. And so there is a equation of motion, which is a direct generalization of the equation of motion of 4-dimensional graviton. And okay, so there is this thing, right? So this equation of motion. And now what we can do, we can dimensionally reduce this equation of motion. In other words, rewrite it from the point of view of Bob. So this is equation of motion for Alice. Alice knows that, okay, this is a massless graviton in 5 dimensions. There is a gauge redundancy in the theory, obviously, with respect to okay, now where gauge redundancy parameter, gauge parameter is a 5-dimensional vector which depends on coordinates x mu and y. Now, since it's a 5-dimensional function of 5-dimensional coordinate, from the point of view of 4 dimensions, this is like infinite number of redundancies. Okay, so not just one redundancy, but infinite number of redundancies, because for each coordinate y, you have an independent function of 4 space-time coordinates. Okay, so the moment we embed gravity in 5 dimensions, a 4-dimensional redundancy becomes infinitely enhanced, which is not surprising because we are adding a coordinate, new coordinate, right, to the story. So now, so from the point of view of Bob, right, what is the story? If Bob thinks in terms of 4-dimensional entities, so Bob thinks in terms of 4-dimensional Poincare invariance, 4-dimensional Lorentz invariance, 4-dimensional Poincare invariance. So Alice thinks in terms of high-dimensional Poincare invariance. Now, up until we compactify the radius, so far I'm not compactifying this radius. I keep y arbitrary. Up until we compactify the radius, 5-dimensional Poincare invariance is unbroken. It's a good symmetry of the theory, and so is 4-dimensional Poincare invariance. Of course, it's just a subgroup. But Bob only classifies things in terms of 4-dimensional Poincare invariance. Now, so this object HAB for Bob, so Bob can classify this object as according to the transformation properties with respect to 4-dimensional Poincare symmetry. Because at the end of the day, we are going to compactify, and compactification will break actually spontaneously 5-dimensional Poincare invariance down to 4-dimensional Poincare invariance plus translations in extra space. But so Bob can right away just classify this object HAB from the point of view of 4-dimensional Poincare invariance. Now, what is it? So this gives us a graviton, okay, when both indexes are, so not graviton, this gives us a tensor, right, symmetric tensor, okay, symmetric tensor. Then we have something that transforms as a, which is has mixed coefficients, which transforms as a vector, and something that has both indices in H in fifth dimension, which looks like a scalar. Okay. Now, so far these are simply transformation properties with respect to 4-dimensional Poincare group. This doesn't mean that these are good degrees of freedom in the sense of good propagating degrees of freedom in the sense of Poincare representation of 4-dimensional group. Okay, so we still have to find out what is happening there. All right, okay, but so far so good. Now, of course, these are not 4-dimensional fields. They all depend on two coordinates, on x and x mu and y, all of them. Okay, just like the original field. And now what we want to do, we want to understand this in terms of purely four-dimensional fields, this thing, okay? So in order to do this, we have to do dimensional reduction. And dimensional reduction is straightforward. It's like a Fourier decomposition. So basically the way we do it, we Fourier decompose field, 5-dimensional field in Fourier harmonics with respect to coordinate y, okay? But since there are indices involved and there's gauge redundancy, we just need to be a little bit more careful. But things are straightforward. So let me choose. So what you need to do, you need to decompose these different components into different harmonics. Choose some complete set of functions. Okay. So actually, if the compactification is simply flat compactification on a torus, these Fourier harmonics, these Fourier functions, the complete set of functions would be simply literally Fourier exponents, plane waves. But let me for a moment keep it general. So let me call them B's, right? So there'll be B functions accompanying, and let me put hat on top of this. Okay, here we have to introduce notations because we cannot get away without notations. So let's watch notations. Okay, so far this is just I'm taking high-dimensional metric perturbation and expanding into Fourier modes with respect to M. Okay. So then we are similarly expanding the vector. But actually, in order to have proper dimensional reduction, so their expansions cannot be completely independent. So in fact, we can, okay, let me choose in the following way that, so the functions B, they form a complete set, okay? Complete basis. Okay, so these B functions of Y. And so let me denote derivative with respect to Y by prime. So prime will be derivative with respect to Y, the extra coordinate. Okay, so let me put prime here. And let me call this a vector with M and X, okay? And so we'll do the similar thing for 5, 5. Except here it's convenient to take second derivative of this object, all right? And call this a scalar phi with it has no index x mu, okay? All right. Now so the B mu functions, they form a complete set, and they satisfy the oscillatory equation, the oscillatory equations, okay? In And as I said, on the flat space compactification, actually, these are just simply plane waves. You can take them plane waves, but we can keep them. Once we have this relation and they are orthogonal to each other, this is sufficient. So this is a completely standard separation of variables and dimensional reduction. So what you need to do, of course, I'm not going to repeat this. It's a straightforward thing. You can do it. It's a nice exercise actually for especially for a student to do it. So you can take this and you can plug it here in this expression. And then notice that this equation has two indices, right? A and B. This equation for the index, and we will get equation for mu nu when AB is mu nu. So we get three equations. We get equation mu nu. We get equation when one of the indices is mu, the other one is 5, and then equation 5, 5 we can also get, right? And so to make the long story short, we can introduce an auxiliary. So now let me explain physics what will happen. So this object now looks like a sort of a spin 2. Is not yet canonically normalized. It's not yet, the kinetic term is not diagonal in this. This looks like a vector, okay, and spin 1, and this looks like a scalar. Now what will happen? So then just tell you the physics. What will happen is that at each mass level, remember we said that massive. So from the point of four-dimensional theory, what we anticipate to obtain, obviously, since we need to obtain representations of Poincare group of four-dimensional. So we have to obtain massive Fierz-Pauli, tower of Fierz-Pauli gravitons, and one massless. Okay, at the massless level, we expect to have Einstein gravity. Okay, so at m equals 0 level, we expect to have Einstein at m equals 0. So m equals 0, we will expect Einstein. At m non-zero, we expect Pauli Fierz-Pauli. Now, at m equals 0, Einstein doesn't require anyone. So correspondingly, at m equals 0, this will get Maxwell. And this was this great idea by Kaluza that tried to unify gravity with Maxwell theory. And we get a scalar. At m equals 0, we get a scalar. But m non-zero, what will happen is that the massive vectors and the scalar, they will get combined with the massive Pauli fields. They will become components of massive Pauli fields. Okay. So in other words, from the point of view of four-dimensional observer, from the point of view of Bob, so what happens is that at each level, the different components of five-dimensional graviton, they combine to form four-dimensional massive gravitons. So the massless high-dimensional graviton at each massive level eats up its own components, okay, the vector and the scalar, and become massive, okay? So at the end of the day, so we can do the following thing. We can, okay, there is one intermediate step for convenience. We can introduce a notation. Let me call it bar, actually. We can combine a mu m with a scalar. Yeah, it's 1/2 is there, convenient for convenience, because this diagonalizes certain terms. And if we write it like this, actually what will happen is that this combination at each level, at each mass level, once we do separation of variables, will give us equation for massive Pauli fields. So in other words, the equation will be like, okay, let's say linearized equation for graviton and and here we'll have Pauli first mass term for for h mu nu. I forgot, we denoted h mu nu with what? With the head, right? Yeah, head. So this will be head. This will be head, Pauli first. So at each mass level, eta mu nu h hat, and then there will be the following structure: d mu a nu m symmetrized, and minus eta mu nu twice the divergence of a mu. Okay, and this. So mu nu equation will have this form. Okay. Now let's analyze a little bit this equation. Okay. So notice that the gauge redundancy is maintained here. So now everything depends on four-dimensional coordinates. And gauge redundancy is maintained. Why? Because at each level, a mu nu hat can be shifted by a symmetrized derivative of arbitrary function xi, whereas am can be shifted. Sorry, this is bar. Can be shifted as by the same vector. Okay. So in other words, remember we had this we had this additional components of the Pauli first Pauli graviton massive, which were vectors and the scalar. Now in this notation, scalar resides in this a bar because we have redefined it. Okay, but as you can see, what happens is that the gauge redundancy is maintained. So the a mu acts like a Stuckelberg. It acts like a Stuckelberg field for the massive Pauli fields at a given level. So at each level, and this is what happens, as we said, at each level, the massive spin 2 eats up the vector and combination of a vector and a scalar, and becomes a first Pauli graviton at each massive level. Okay, and so then there is another equation, which is equation with one index, right? So, and this equation looks like a Maxwell equation, which not surprisingly, because remember we had the vector, they are floating around. Okay, and actually has this form h. Okay, so what do we have? We have first Pauli, and here we have Maxwell-like equation. Sorry, not Maxwell-like. The no, sorry. So this is okay. This is equation is Maxwell-like. Maxwell-like with a source. So this is it's like an effective source. Okay, so now let me describe the following view on this. So now at the massless level, sorry. Does every level M of the tower have the same number of degrees of freedom? Yes, exactly. Every level M has the same number of degrees of freedom. So in other words, so what is happening is this, that, okay, we have this tower, right? Let me write it in a discrete form, because so far I didn't compactify. Let me write it in discrete form. So what happens is that at each level, we have 5 degrees of freedom. So at each level, M, we have 5 degrees of freedom. Now, the 5 degrees of freedom are, so at this, including 0 level. At the 0 level, we also have 5 degrees of freedom. So the 0 level, this is M equals 0, okay, M equals 0, also 5 degrees of freedom. Now, however, at non-zero level, the 5 degrees of freedom, they combine themselves in form of 2 plus, okay, let's write it as 2 plus 2 plus 1, okay, in form of First-Pauli graviton. And at the, so this is First-Pauli. And here they are separate. So this is Einstein, this is Einstein, this is Maxwell, and this is just an additional scalar. Actually, this level was why Kaluza introduced this idea of extra dimension to unify Einstein gravity with general relativity. So Maxwell is a level 0 component of this tower. So this is Kaluza-Klein tower. Kaluza-Klein tower. Okay. Now notice the following thing. So if we go to higher number of extra dimensions, there will be additional degrees of freedom. Okay, there will be additional vectors and additional scalars and so on. Okay, so but in 5, this is what we have. Okay, does this answer your question?
Yes, it does. Thank you very much.
All right. So now I want to make one remark, which is sort of interesting. The remark is the following. So, okay, now now we compactify. Okay, so once we compactify, we get precisely a discretum of tower. Now, since one dimension is compact, the y dimension is compact, what happens is that we get periodic boundary conditions, right? So the fields now are periodic. And because of this, the momentum, a conjugate variable, becomes discretized, becomes quantized. So the mass, therefore, becomes as integer in units of the radius of compactification. So this is compactification radius. Okay. So now, what happens with original Poincare symmetry when we do this? So original Poincare symmetry is broken, but however, it's broken spontaneously because the compactified space is a solution of the theory. So we are breaking symmetry by choosing a solution, by choosing a vacuum. Okay. So the way you can think about it is like this: the initial theory has all possible radii of compactification. There is a limit in which we decompactify, in which we move towards simply infinity, and each configuration is a choice of the vacuum. Okay, and correspondingly, what happens is that the Poincare 5. Okay, let's call it Poincare 5 is effectively broken down to Poincare 4 and times the translation in on a circle. Okay, times translation on a circle, which is U1 basically. Okay, U1 symmetry. So this is of translation in y direction. Okay. Now this symmetry translation in y direction, from the point of view of a 4-dimensional observer, this is like an internal symmetry. So Bob cannot tell now the difference between internal symmetry and space-time, because space-time is for Bob is like 4 space-time coordinates, and U1. So Bob thinks that there is a theory in which there is 4-dimensional Poincare symmetry and U1. Okay, and correspondingly, there is U1 and there is a massless graviton, in 4 dimensions, and there is massless. There is a massless vector, okay, in 4 dimensions. There is also a massless scalar at the 3 level, okay. Now, there is an alternative interpretation of this this y vector is massless, and because think in terms of Goldstone theorem, okay. Now, if I'm breaking 5-dimensional Lorentz invariance down to 4-dimensional Lorentz invariance spontaneously, from the point of 4-dimensional Lorentz invariance, so you are expecting to have a Goldstone boson, which transforms as a vector from the point of view of 4-dimensional Lorentz invariance. So you can also think about this vector, a Maxwell, okay, as a Goldstone. That's one way to understand why there is a massless vector once you compactify. Okay. Well, this is just an interpretation. It's sort of okay. Doesn't add much to calculation abilities of the theory, but okay, it's an interesting interpretation. Okay, so now we will arrive here to the following conclusion. So you see, you can now let's restore dimensionalities, right? If we restore dimensionalities, if we start with 5-dimensional action, so it will have integral dy, then d4x, and then here we'll have so we used canonically normalized, so non-canonically normalized graviton, right? So we had the okay, we have this type of so the inverse, so Newton's constant in 5 dimensions has dimensionality of 1 divided by mass cube. So this is a fundamental Planck scale. So I'm denoting it by m star, because this is now the fundamental cutoff of the theory. Okay, we are in pure gravity. Now, however, once we dimensionally reduce this theory, what do we get? We get that there will be an effective Planck mass. Okay, in 4-dimensional theory, we should get effective Planck mass, d4x integral. So effective Planck mass, 4-dimensional Planck mass, what we call Planck mass, and then 4-dimensional graviton plus the rest, right? Again, dimensionless perturbation of the metric. So there is a relation, as we can see very easily, that effective 4-dimensional Planck mass is integral of dy from 5-dimensional Planck mass cubed, or in other words, this is 5-dimensional Planck mass square times Planck mass 5-dimensional times the compactification volume. Okay, of course, here there is a 2 pi also. So, okay, we can write it as 2 pi. All right. Now this, this relation actually is nothing but the relation between the gravitational cutoff and the number of species. You can notice this immediately, because this number is simply a number of Kaluza-Klein species. So because the spacing of Kaluza-Klein, the mass of Kaluza-Klein species goes like n over r, and if you count the number of Kaluza-Klein species, so this is number of species and species from 0 to the cutoff. Okay. Now this generalizes to arbitrary number of to an arbitrary number of extra dimensions. So basically, this relation that now if I have n extra dimensions, we will have the same thing. So the 4-dimensional Planck mass square is 5-dimensional is fundamental Planck mass square times the phi m star in units of compactification volume. Okay, in the compactification volume of n-dimensional internal space or d-dimensional internal space, let's say, okay, times m Planck. And this quantity is always number of Kaluza-Klein species. So, in other words, the Kaluza-Klein theory or large extra-dimensional theory simply as a particular case of when the existence of large number of particle species lowers the cutoff of the theory, gravitational cutoff of the theory, as relative to the Planck mass. So this relation is universal, okay? And so here it's explicit, all right? So now, this tells you immediately that if you want to have the fundamental cutoff around TV energies, the compactification radius must be large. Now, larger is the compactification radius, larger is the number of Kaluza-Klein species that can fit within this compactification radius. And so this number is invariant. It has to be 10 to the 32. So whatever construction we do, this compactification, large volume compactification, number of species must be 10 to the 32 in order to for this to be relevant for understanding, for the addressing the hierarchy puzzle. Okay. Of course, the relation is true for arbitrary compactification radius. This is universal relation, but for the hierarchy case, for addressing hierarchy, this number has to be large. This is what I meant when I said that in large extra dimensions, this number is there, but it's hidden in the compactification volume. This number is always hidden somewhere. Okay, obviously, when you need to have a hierarchy, there is a number. So whenever we want to explain the hierarchy between the Higgs and the Planck mass, we have a number, we have a large number, and this large number has to come from somewhere. Now, there are approaches, which unfortunately I cannot cover in these lectures, in which this number is a result of dimensional transmutation. Okay, so for example, this is the case in warped extra dimension, other Randall-Sundrum type extra dimension, or also in 4 dimensions, we can have dimensional transmutations. There are proposals in which weak scale can originate as a result of dimensional transmutation. Somehow we generate weak scale as 1 minus some small number, some small scale, some small coupling times the big number, let's say Planck scale. Okay, so of course in that case again we have this number. I mean, if we square it, we have to get 10 to the 32. So the number has to come from somewhere always. Okay. Okay, so let me. If there are any questions about this, and so we have about like 20 minutes remaining, right? So let me take questions about this, and then I will make some final comments, final discussion. There's another topic I wanted to touch, but okay. If there's anything so far. Okay, so I mean, final comments. Okay, the comments are, if, again, I only touched one particular aspect of the hierarchy problem and one particular view on possibility how to address this problem by lowering gravitational cutoff around TV energies. Now, okay, nice thing about this type of answer to the hierarchy problem is that, of course, it comes with a prediction that if the cutoff is nearby, and in particular, if we can probe these cutoff energies in colliders, then the prediction, so prediction are resonances or quantum black holes. These are not ordinary black holes, obviously. So these black holes, the black holes, if we are lucky, so, and LHC can probe gravitational cutoff of the theory, what we will the way this will manifest itself, we will see some resonances. Some resonances that will, at the bottom of the tower, so we should see some tower of resonances, okay? So tower of black hole type resonances. So tower of black holes. Now, the point is that there is a spectrum of black holes, right? And above the cutoff. And so what the signal that we are touching, gravitational cutoff, expected signal, is the following. At the bottom, we will see a resonance. And it will be an extremely hard, I think it will be simply impossible to, if LHC can only probe the bottom of the tower and first resonance, from there to really conclude that this is not just another particle, okay? Because, as I said, the first resonance is very far from being a classical black hole, or very far from being semi-classical black hole. It doesn't have really large entropy. It doesn't really have entropy. It can be like few states, but it's hard to call when you have a system in few possible states an entropy. Entropy is a large N notion. And so correspondingly, what will happen is that we'll see a particle, okay? So a resonance that will decay. Now, so by unitarity suggests that if we produce resonance in collision of two quarks, then decay back into those that produce this resonance should be appreciable. So in other words, so if you ask me, I would expect this resonance to decay if this has anything to do with gravity, with quantum gravity. It's with high probability should decay back into let's say if we form it through quark-quark, so it has to decay back to the same quarks, and so the signal should be some kind of two jets, okay? So this will be characteristic signal of this type of resonance. But of course, there would be no way to prove that this is necessarily a beginning of black hole tower and not just another particle which decays into two jets. So now, in order to probe quantum gravity, to catch glimpses of quantum gravity, we will need to go significantly above first resonance. And then, then this would be possible, because if you manage to go significantly higher than the first resonance, then everything I discussed suggests that what we should see a next resonance, and the higher and the heavier is the resonance. So the heavier resonance. So if I have a resonance with mass m larger than m star, okay, it cannot be really much larger with the present capacities of the accelerator, but somewhat larger, okay? Must be longer lived. And decay into more quanta, more number of softer quanta, okay? So in other words, so the black hole-ness type properties should gradually set in, okay? So the first resonance, okay, it's like a particle. Next resonance with a little bit longer lived, decays into softer stuff. So more and softer. And of course, eventually, if the accelerator would have arbitrary capacity, we could even form a black hole, which is classical in a very good approximation, and then that would be already a classical black hole. But so this is the characteristic signature, that we are touching at the cutoff of quantum gravity, because it has to soften above that scale and become, so the theory from everything I said it's expected to be theory of extended objects and of softer and the objects that decay into more stuff. Now, of course, what could happen is that if the ultraviolet completion of gravity, so there are two things that are important to understand. That, for instance, ultraviolet completion of gravity, such as, for instance, string theory doesn't change deep UV properties of gravity. Okay, so in string theory, if I do collision of strings, two strings, the end result, if the center of mass energy is very large, the end result is again multi-soft graviton state. So sooner or later, if you arbitrarily increase center of mass energy, string theory is also dominated, is expected to be dominated by black hole production in deep ultraviolet. Okay, so string theory doesn't change the fact that deep UV gravity becomes again infrared gravity, because in string theory, of course, we have black holes because string theory incorporates Einstein gravity. So therefore, this statement that in deep UV at very high center of mass energy, the gravitational amplitude should be dominated by multi-particle soft amplitudes. That statement is invariant, is insensitive to what happens with the UV completion of gravity around Planck scale or below Planck scale. However, the signatures at low energies will be different, obviously, because if we see, let's say, we have fundamental Planck scale here, and if we have string coupling, which is sufficiently weak, so in string theory, there is a relation, there is a hierarchy between gravitational coupling and between the Planck mass and the fundamental string scale. Okay, so so for instance, in 10 dimensions, so we have 10-dimensional Planck mass is related with the string scale and string through 1/G string. Okay, so if G string is very weak, okay, then the string scale is below the fundamental scale. Okay, so this cutoff could be fundamental Planck scale, fundamental Planck mass. And so it may happen, of course, it may happen that the accelerators first probe the string scale. And of course, then here, in this case, there will be, the prediction is that there should be a very clean signature of string resonances of here in this interval, string resonances should be produced. Okay, now string resonances can be computed, has been computed. I mean, there is a literature. But by the way, I will give references to topics and some original papers separately. Yeah, this have been computed, and it can be computed at weak coupling, because if string theory weakly interacting around string scale, so it's a weakly string perturbation theory works, so we can compute that. Okay, this thing, and in that case there will be string resonances, the signal. So yeah, so therefore this is as far as signals of the solution of the hierarchy problem by lowering the cutoff is concerned. So unfortunately, LHC we cannot produce the energy of LHC is not enough, is not sufficient for producing a black hole which is sort of well classical. That cannot happen. So the first resonance will be like a quantum particle, as I said. So it will not, its decay of this particle will not be anything like Hawking evaporation, okay? Only if we can probe higher resonances, then we have a chance of seeing some softening of quanta and moving towards more Hawking-like evaporation. But unfortunately, the capacity of LHC, that's not sufficient. Of course, if LHC can touch the bottom of the tower, even if we cannot fully interpret it, but we will see some new particle, that will be an extraordinary discovery, obviously. Okay, and then we can worry about understanding what is the role of quantum gravity later in that. Okay, okay. So let me take some questions about this.
Hey, I may I ask a question? Sorry for.
Yes, sure. And then there's also in the chat. Yes, please. Of course.
So what makes us think that the transition is going to be smooth between these kind of hard decay products into soft decay products and not like some sort of phase transition?
Oh, sure. I mean, there could be some so the smoothness. So things as sharpness of the transition and smoothness of the transition. These are quantitative questions. So we have to quantify. So what do we mean under smooth or sharp? So yeah, I mean, so the transition could be sharp. So in other words, the regime change could be pretty abrupt as a function of, for example, center of mass energy. Okay, in the collision. Let's say you have head-on collision. Let's assume head-on collision, right, between quanta, the head-on collision, and and here we're producing this tower, okay, and so the question, so the question you are asking. So first question is, what about producing the bottom of the tower? So the first resonance, that we just expect like should be similar to, spiritually should be similar to production of QCD resonances. Okay. Now, of course, to make this more precise computation here, we need a microscopic theory, because you see, in general, in physics, well, actually, this goes beyond physics. Usually, questions all the questions that we're asking is always within some framework. We cannot ask questions independent of the framework. So therefore, whenever we're asking some questions, we are trying to come up with an answer, we assume some framework. So there are certain set of questions. For example, the question of what is precisely the property of the resonances around the cutoff. That question is impossible to answer without having a microscopic theory. So this requires a microscopic theory. Okay, so this requires a microscopic theory that allows you to do some calculations. Okay, and this is very important to understand, because you see, you may have some microscopic theory. You can offer me, say, look, here's my theory. This is what we. And I may say, okay, I'm skeptical, or look, this is interesting, or something. But that's the next level. So in other words, we may agree or disagree on microscopic, on the validity of how good this microscopic theory is. But as a starting point, you need a microscopic theory. We cannot compute things without having a framework. Now, there is no commonly accepted microscopic theory. First of all, there is no microscopic theory which does understand as the structure of the resonances around the strong coupling, and also there is no microscopic theory of the resonances of these resonances that we commonly accepted. Now, one way to do these computations, I mean, would be to extrapolate them from the better understanding that we have for black hole resonances that are heavier. Because remember, I mentioned these 2 to the n scattering processes, okay? Now, these 2 to the n scattering processes, these computations can be done reliably in this kinematic regime. They can be done reliably both within effective field theory and within string theory. So there we know what is happening. And there we see that these computations, they correctly reproduce certain aspects of black holes that we expect. For example, we know that at the point of each microstate for this production is suppressed by precisely what would be the black hole entropy for these microstates and so on. So therefore, one strategy would be to extrapolate to understanding smaller black holes from large multi-graviton resonances, decreasing the number of gravitons. So in other words, if you think of black hole final state as sort of a loose bound state of soft gravitons, then you say, okay, this looks promising, and now let's move towards trying to understand smaller black holes as bound states of harder and less gravitons. So for example, 2 graviton bound states. By the way, such computations have also been, such attempts have been done to computing this spectrum, and then extrapolate from there. So that's one strategy, for example. Okay. Now, as I said, in the domain, because you see, for large black holes, we can use in physics. The problem is that rarely that we can compute things exactly. Normally, we always do expansion in some parameter. For large black holes, we have such a quantum parameter. That's the entropy, and or which is the same thing as occupation number of gravitons within this particular approach. So we have this parameter, so we can do expansion in 1/s, and we can do computations in 1/s expansion. But once we are at the cutoff of the theory here, the S, you cannot even define it because it's order 1. Right? I mean, the object that has entropy equals 1 is not really an entropy. An electron can be, let's say, in 2 states, spin up and down, but to call that an entropy, it's a little bit a stretch. Why? Because the corrections 1/s are large, are order 1. So correspondingly, here one needs to find some good expansion parameter. And I said, this is not specific of gravity, this problem. We have exactly the same problem in QCD, despite the fact that we have enormous data in QCD. We can do experiments, etc. We are out of the computational abilities right at the cutoff. So here we are facing the same problem. So therefore, I don't know whether this answers your question, because these questions are impossible to really answer. As I said, we can try our best to extrapolate from what we understand. In quantum theory, we always compute things in certain domain that we understand, with certain assumptions about microscopic structure, and then try to extrapolate and do our best. Okay. So yeah, so that's what makes us think. If we extrapolate, for example, from computation of QCD resonances, QCD type resonances, then we have some ideas how sharp these transitions should be, and looks like, yeah, they should be similar to having resonance tower. Okay. I hope this answers your question.
Yeah, thank you very much.
Okay, so there are some questions in the chat. So there's one question: what about gravitational waves? Would they be able to probe this scenario? So presumably the question is about gravitational waves that have been observed in the black hole mergers, okay, in the binaries. So if the question is about, of course, any emission of graviton, if we produce gravitons at LHC, you can think of them as micro gravitational waves, obviously. It's okay, that will be part of it. But I understand the question is about these macroscopic gravitational waves. So with macroscopic, so there is a general issue, and this is not specific to gravity, how to probe quantum substructure by observing macroscopic waves. Okay, so again, the story is similar, because the gravitational waves that we're observing, from the point of view of theory of Einstein gravity, weakly coupled Einstein gravity, they represent coherent states of gravitons with certain mean occupation number of gravitons, which is astronomically large. Okay, so n is enormous, much larger than 1. correspondingly, probing quantum substructure already at the distances of the characteristic frequency of those gravitational waves would mean that we can probe effects of 1 over n. Now, when 1 over n is very small, in order to probe effects, we need some enhancement. For example, we can overcompensate by having huge time scale for the experiment and repeating experiment over and over again and having like infinite precision. Then we can overcompensate this type of suppression. Okay, or we can have some other enhancement effect of this effect. Now, this is regarding 1 over n effects at the scale of frequency of those gravitational waves. Now, unfortunately, to probe cutoff physics with those frequencies, another issue is that the frequency of those gravitational waves is way below of any sensible cutoff of quantum gravity where gravity becomes strong. Okay, and so again, we have the same story there, that without having a precise microscopic theory that would somehow relate cutoff physics with macroscopic observations, we cannot really say that we can probe this cutoff physics in gravitational waves. But within a concrete microscopic theory, if you have one, for example, then you can make predictions and you can say, look, my microscopic theory predicts this and this for macroscopic waves, and so you should see this effect. And then, yeah, then it will be possible to probe it. I'm not aware of anything which is easily probable at the level of present accuracy, but future improvements, yeah, there are some ideas that could be very interesting. Yes. Mm-hmm. Okay. Okay, there is another question. Are you saying that close to the cutoff, the black holes are unstable and can decay into quants? Well, black holes are unstable in general. So the black holes decay, as we know. So the Hawking radiation is a decay of a black hole. So even a macroscopic black hole, and that decay is extremely well understood. So you can think of it as a Feynman diagram. So here's a black hole, emits a quantum and goes into black hole with a smaller mass. So there is a black holes decay all the time. Okay. So black hole goes into black hole prime, and here is some quantum, let's say a photon. So black holes decay, sure. With the rate that I gave you, the rate for the mass decreases by the rate of Stefan Boltzmann law is this. So the emission rate is given by the thermal rate here. Now, when the black holes are close to the cutoff, they are no longer black holes. That's why I'm always very careful. I don't want to call them black holes because they are quantum objects. Okay, so I would call them beginning of the black hole tower of quantum black holes. So because they are quantum, their decay rate is correspondingly extremely large. So their decay rate is comparable with their mass. So they decay almost instantaneously. Okay. So yes, they are unstable, and we expect them to be unstable. Of course, you can have particles around the cutoff scale which are stable because of some conserved quantum numbers. Sure, I mean, there can be such particles, quantum particles, which are stable because of conservation of some gauge quantum numbers, stuff like this. That also can happen. But in the absence of these conserved quantum numbers, yes, the resonances are expected to be unstable. Yeah, similarly to unstable QCD resonances. Okay. I don't know. I hope this answers your questions. This was Sylvia's question.
Yeah.
Okay. So no, these are extremely important questions.
There is another question. I don't know if you want to leave it to the afternoon or.
Sure, we can also leave it to the afternoon. Yeah, I don't know. There is only yeah. It's I can maybe try to say briefly reply, just not to ignore it, not to ignore a question. And so Leonardo's question, right? Yes.
Yeah.
So if one or more ultralight fields with mass were discovered, would you propose it still be possible? So the question is, if one of or more ultralight fields with mass less than electron volt were discovered, would your proposal still be possible? Well, okay, I didn't make. I tried not to make really a proposal. I just tried to explain things. None of this that I said is a must, obviously. As far as solution to the hierarchy problem is concerned, that's one possibility. The other relations that I tried to explain, these are relations that follow from QFT and from duality QFT. I don't see what is the connection between having a, I mean, yeah, for example, photon has mass which is much less than electron volt. No problem. I mean, there could exist another particle with mass much less than electron volt. In which sense there is a connection? I maybe you could specify more. I mean, given that we already have particles which are lighter than electron volt. So yeah, so maybe you could specify.
If I can clarify, so the reason was trying to understand the behavior of alpha gravity as you get closer to m star. So if I understood correctly, the sharpness is dictated quite strongly by the extent to which new degrees of freedom show up close to m star.
Correct, yeah, exactly. That's absolutely correct.
So let's assume that we have 10 to the 34 ultralight scalar fields. That would imply that alpha gravity becomes already quite large at
around the TV scale.
Already, okay. But not
yeah, so if you have, you can, so in our universe currently, we don't know how many fields are there. We can only put a bound, okay? So we can have, what I'm saying is that we have a very sharp upper bound on the number of particle species that exist, the total number of particle species that can exist in our universe. That bound is very sharp. That's 10 to the 32 approximately. Now, those particles may be completely decoupled from us and only communicate by gravity. Okay, so there is no need to discover those particles in our everyday experiments. They can be just floating there. They can even be massless, all of them. But no matter what, if they exist, because they couple to gravity, the cutoff of gravity will be lowered around TV scale. Okay, so this is what I was saying. So yeah, so then the rest depends on how strongly these particles interact with us. No, for example, they can also interact with us non-gravitational in principle. In plenty of extensions of the standard model, you have huge number of particle species, which are in the hidden sectors, non-hidden sectors, and so on. So yeah, so it will depend on that. Yeah.
Okay, thank you.
Okay, thank you. Okay, so then we can postpone the rest to the discussion, probably, right? Because
okay, yeah.
We have a discussion, right, today?
Yes, we will have a discussion as usual at 5:30, and actually will be all for you because Professor De Cogenon has a problem attending this afternoon.
Oh, okay.
Okay, so, but I would like to thank you a lot for this very, very interesting.
Well, thank you very much. Yeah, it's a pleasure.
Yeah, I would like to invite all the others to join me clapping and.
Thank you.
They were very, 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 very interesting.
Thank you very much. Thank you. I'm very happy to hear that.
But we will.